And our second invited speaker is Dr. Peyman Milanfar. Peyman Milanfar is a principal scientist and director at Google Research, and he leads the computational imaging team. And prior to Google, he was a professor at UC Santa Cruz. He has won many best paper awards and is also a distinguished lecturer of the IEEE Signal Processing Society and a fellow of the IEEE for the contributions to the inverse problem and super resolution in image. And we are very happy to have Dr. Milanfar here.
All right, yeah, thank you. Thanks again for inviting me. Pleasure to be with you. So I'm going to be speaking about denoising today, and this may be a good time to mention that I think denoising plays a really key role in sort of all areas of computer vision, even though it's not very broadly acknowledged. So hopefully this will be both a little bit of a tour of denoising and motivate folks to look more carefully at this problem, which I think is also in machine learning is becoming quite prominent. All right, so let's go ahead and get started. All right, so denoising really, we're talking about here the simplest of inverse problems. You have a clean signal. It has been corrupted by noise. In this case, we can think about it as Gaussian, but it may be more general. And we make a measurement X, and the idea of denoising, of course, is to just design a filter whose output is as close as possible to the underlying image as we can. Okay, so easy enough to state this, but not easy enough to do. However, denoising is one of those areas of imaging that has really impressively delivered over the last several years. In fact, if you look at, so here's an example of before and after images, we can now do denoising of a typical image that comes out of a smartphone, which might be 10 or 12 megapixels in a few hundreds of milliseconds with nearly state-of-the-art quality. And that's really kind of unprecedented for these kinds of applications. I want to give you a little bit of a quick overview of denoising history. Denoising is really one of the very first problems that was addressed in image processing, and you could say low-level computer vision, from the very beginning of when these things actually became technical issues to deal with the US space program in the 1970s. Initially, much of the work was largely heuristic. Things like the Wiener filter, as very simple L2 regularization-based methods. Robust statistics were introduced in the 90s, PDE methods, diffusion, wavelet-based methods, and then the bilateral filter was introduced in the very late 1990s. Self-similarity methods like non-local means and its various cousins were introduced later. Point regression methods, sparsity methods, and now, of course, in the last 5 or 6 years, neural networks of all sorts have been introduced. So I'm going to give you kind of a bit of a taxonomy of everything that's available and talk about these things in the context of many of the applications. But first, let me step back to about 10 years ago. My student Priyam Chatterjee and I wrote a paper, I think this was in 2010, and we asked the question, is denoising dead? And this was at the time a rather provocative question. Maybe it's not so controversial nowadays. But the idea here was that at the time, at least, and this has grown steadily, many thousands of papers had been written about denoising, and very different algorithms were basically yielding very similar performance. And we did some analysis that showed that the performance of almost all the algorithms very, very close to the best possible performance you could get in the mean squared error sense. And we did this with some relatively fancy statistical bounds modeling. Now that gap, I think, as far as nowadays is concerned, has been basically closed with the neural net methods. So the bottom line is that image denoising is, at least nowadays, more or less a solved problem on its own. But what else can we do with denoisers? So that kind of, it gives us a tool. This is something that works really well. It's practical. We can do a lot of great things with it. But what are the things that are outside the domain of just removing noise? And so that motivated a lot of the work that we did in the last few years. Okay, so let me give you a little preview of what kinds of things denoisers can do besides denoising. It turns out we can leverage denoisers to solve much more general inverse problems. For example, things like tone enhancement, HDR imaging, deblurring, super resolution, and many, many other things. So here's a somewhat provocative example, unexpected, I would say. So the image on the left is a blurry image, and the image on the right is the recovered image, the sharp, an approximation to the sharp underlying image. And the real engine that was used in this reconstruction is a median filter. Now, I don't know about you, but I would be hard pressed to believe before I did this work with my colleagues that a median filter could be used to do deblurring. But nevertheless, you have it here. I won't explain exactly how that was done yet, but I will later on in the talk. So this is it. Consider this as teaser for now. Okay, so general denoising filters. So what we think about denoisers as a function that maps the interval 0 to 1 crossed with itself n times. So it's an n pixel image to the same interval. So the reason why I'm picking this compact interval as opposed to just all of the real line crossed with itself, or Rn, if you like, is that images don't have arbitrary values. So for example, if you have an 8-bit image, you have 256 gray values. So for convenience, I'm just going to think about these in the range of 0 to 1. And so now we have this class of functions that take one compact set and map it to another. So let's think about what makes this class of functions special. And here I'm going to start kind of giving a taxonomy of the different kinds of denoisers. Let's start with general nonlinear denoisers. The first class that I want to talk about are so-called pseudo-linear denoisers, and I'll make this definition a little bit more clear in the very next slide. So this includes things like non-local means, KSVD, BM3D. These are all very well-known algorithms, and they've been developed over the course of easily the last 15 years. Bayesian denoisers and their approximations, including things like maximum or posteriori, including KSVD, or minimum mean squared error, which include Wiener filter and various approximations of it. And then other, and this here I'm kind of lumping many things together, including PDE-based methods and CNN-based methods that don't necessarily obviously fall into these two other categories. All right, so let me talk about pseudo-linear denoisers first. So let's forget about pseudo for a second and think about linear denoisers. Linear denoisers are simply just low-pass filters. You're taking some pixels here in the input image, and you're computing a weighted combination, a linear combination of the input pixels to give you an output pixel in the denoised image. Now, if you just go one step further and allow the weights here to be dependent on the pixels on which you're operating, now what you have is a pseudo-linear denoiser. In other words, it retains this structure of a weighted average, except that the weights depend on the pixels on which you're operating. To be a little bit more mathematically clean and concrete about this, let me write everything in matrix form. So let's take one output pixel indexed by I and write it as a linear combination of all the input pixels. Now this seems a little bit absurd because we typically don't use all the pixels in the input to give an output pixel, but it's just as easy to write it in this way so that we can have a matrix description. So these weights can be the weights that point to a specific output pixel, can all be collected and gathered into a row vector like this. And I'm calling that bold WI transpose. And then I can take all of these weights and stack them into a matrix. And that matrix I'm going to call W. And so the form of the denoiser effectively is going to be W times X, W being a large matrix, N by N, and X is effectively the image that has been stacked, scanned and stacked into a long vector. Now, if W is not a function of X, then you've got your simple linear filter. And if Wx is a function of X, you have your so-called pseudo-linear filters. Let me give you an example of what these weights might look like, these non-local weights. So take these two pixels, the blue and the red pixel, and I'm going to compute similarity between this blue pixel and all the other pixels in the image. And then I'm going to take this red pixel and compute the similarity between that and all the other pixels in the image. And I'm going to get two images. If I take these two images and scan them into a row, each of these images, this one on the left and this one on the right, are going to give one row in that matrix W that I just talked about. So that's kind of a graphical description of what these are going to look like. So pseudo-linear filters, it turns out these are approximations or empirical Bayes approximations. This has been shown in a number of different papers over the years. And again, to repeat, they have two stages. They have a nonlinear stage, which is the stage where the weights are calculated. That's W of X. And then once the weights are calculated, the weights are fixed. And then at that point, it's simply a linear filter where W is applied to X. This formulation turns out to make the analysis of these filters rather convenient. And I'll talk a little bit about that later. Okay, so what are some of the properties of this W of X that we can have? First of all, the matrix W, it turns out, is approximately symmetric. And I say that because you need a proper sort of normalization in order to make sure that W is symmetric. If you simply take the weights pointing to a pixel and normalize it by the sum of those weights, then you don't really get a symmetric matrix. But there are various technical tricks to make it symmetric. And that turns out to be very convenient. The spectral radius is less than or equal to 1, which means that these filters are non-expansive. If you're more comfortable with sort of the signal processing point of view, you can think about the spectral radius being bounded by 1 as effectively these are low-pass filters. So they're essentially going to remove some energy from the image. And because they remove some energy, they're essentially non-expansive. It turns out the eigenvalues of these filters, regardless of whether you're talking about W being dependent on X or not, they decay very quickly. One other thing worth doing here in terms of a definition is we can define a Laplacian. And a Laplacian action on X is simply the residual of the filter. So you apply the filter and then you subtract what you just applied from the original image. And what you get is I minus W applied to X. And I'm going to write I minus W as L of X. All right, so now let's move on and talk about MAP, maximum a posteriori versus minimum mean squared error. Both of these are going to depend on this posterior density, P of U given X. Again, remember X is equal to U plus E. The MAP estimate basically takes this posterior, I've sort of drawn a cartoon of it here, and thinks in terms of the peak of that distribution. The value the argument that maximizes this is basically the one that gives you the peak of this distribution. That's the MAP estimate. The MMSE estimate is a little bit different. The MMSE estimate is the expected value of this distribution. So in general, it doesn't coincide with the MAP estimate unless the width of this distribution is very, very small, or correspondingly, if the noise is very, very weak. But in general, they're very different things. All right, so let's talk about MAP denoisers in a little bit more detail. So when you're computing the MAP denoiser, you have two terms. The first one is this squared norm of U minus X, and that basically is capturing the data fidelity term or otherwise indicating the fact that your noise is Gaussian distributed. And the second term, phi of U, is the negative log of the prior. Prior here is P of U, which was a distribution, the prior distribution that you have in mind for your image. Now, some of you may be familiar with a different language of proximal operators. And if you look at this is basically the MAP denoiser is nothing but a proximal operator, specifically when phi is convex. Although in our case, we're going to take the general approach of thinking of phi as not necessarily convex. Okay, so for the case where you have this, it turns out there's a really nice way of rewriting. It's kind of a closed form, but not quite exactly, but let me explain without going into too many details. It turns out that if you look at the theory of proximal operators, one way to write this a solution of this optimization problem is that it can be written as X minus sigma squared, this is the variance of the noise, times the gradient of phi of X, except that this is not quite phi of X, is a smooth version of phi. And this smooth version is something called the Moreau envelope. Let me give you an example of what this looks like. So suppose this phi is in fact this L1 regularization. So this is just an L1 norm, okay? Now, if I compute the Moreau envelope of this, you get this red curve, which is the Moreau envelope of the L1 function, of the L1 loss. And it turns out this is precisely the so-called Huber loss, where here between -1 and 1 is a quadratic, and then outside this region is linear. This is the so-called L1, L2, or Huber loss. And now if I compute the gradient of this and do x minus sigma squared, the gradient of this red function, what I get is precisely this soft thresholding, which you should all be familiar with as the result of using L1 to regularize the denoising problem. Okay, what about MMSE? Now, with MMSE, things are a little bit more complicated, of course. If you look at this, you realize that you have this kind of nasty integral on the right-hand side that you need to compute, and oftentimes it's not possible to compute it in closed form. Now, a result that may or may not be well known to many of you is something called Tweedy's formula. This is a really remarkable formula, which effectively removes the need to have explicit access to P of U or to U at all. Remember, U is kind of the underlying image that you don't have access to anyway, but presumably you think you would know the prior. Here, it turns out to actually compute this MMSE estimate, you don't need access to that prior directly. All you need is P of X, which is the marginal density of X. And this marginal density, remember, because X is equal to U plus noise, this marginal density is a blurred version of P of U. And it's blurred with a Gaussian, right? So you don't have access to the original the prior, you have access to a blurred version of the prior. Now, if you just kind of carry through with this, you can write this right-hand side, of course, as X plus sigma squared gradient of the log of P of X. And it turns out you can again rewrite this as X minus sigma squared gradient of, again, phi sigma X. But now I put a tilde here because this is, again, a smooth version of phi, but it's yet a different smooth version of V. This time it is a blurred prior. It's negative log of the blurred prior. So the reason I'm going to all these lengths is to show you that these estimates, despite the fact that they're very different, they actually have a very similar form. So here's another example. Again, we start with L1. We compute this smooth version. This is a differently smooth version than the L1, L2 loss that you saw before. And then if I take this gradient and X minus that sigma squared times the gradient, I get the smooth thresholding. And I'm just going to put these on top of each other so you can see the map estimate here is the soft thresholding, which is discontinuous. And then the MMSE estimate is a smooth thresholding, if you like, which you see here in the red curve. Okay, so let me summarize what I've said so far. The pseudo-linear denoisers have this form f of x equals wx times x. And if you remember, I mentioned that you can write this as x minus the Laplacian acting on x. The map estimate can be written as x minus sigma squared gradient of phi sigma. And this phi sigma is a Moreau smooth loss. And then finally, the MMSE estimate can also be written as x minus sigma squared gradient of phi sigma tilde x. And this is just a differently smooth version of phi. Now, what I want to do here is to bring your attention to the fact that all of these have the following form. They're of the form x minus something of x. And in fact, you can really think about denoisers as a perturbation of identity. The shrinkage interpretation is obvious from the last two lines here. You can also think of them as a gradient step, right? So this is like x minus sigma squared gradient. This looks like gradient descent, essentially. Now, I call these a perturbation of identity because think about what happens if the noise isn't there, if the noise is basically asymptotically zero, if the variance of the noise goes to zero, what should a denoiser do? The denoiser should do nothing. It should just replicate the signal that it comes to it and reproduce it exactly, which means that it has to behave like an identity operator. So as your noise grows away from zero, then the denoiser becomes a perturbation of identity, and it's a stable perturbation of identity. Okay, so let's think about it one more way, and I think this is really helpful. You can think about the denoiser as f of x equals x minus v of x. And v of x here is just some vector field as a function of x. Another way you can think about actually designing denoisers from scratch is to consider V of x to be defined very generally as a gradient of some energy function, right? So start with some energy function that you like, take its gradient, and then that's V, and then x minus that, you can think of that as basically defining a very broad class of these kinds of filters that we talked about that we call denoisers. Now, if I were to put this into this general framework and pull this gradient sign outside, what I have if f of x is equal to the gradient of 1/2 norm of x squared minus e of x, or gradient of e bar of x. And this e bar is sort of the complement of e with the x squared subtracted off. A useful side effect of defining denoisers this way is that they define a conservative vector field. So the reason why is because f of x is the gradient of a scalar function. And so by definition, it has to define a conservative vector field. And furthermore, the gradient of f of x has to be symmetric. This turns out to be of technical interest later on when I talk about using denoisers as ways of regularizing inverse problems. Okay, so it turns out I haven't really said much about how the w of x times x formulation fits into this, but I'll say a little bit more about that later. So bear with me while we get to that. Okay, so this is really something important that I want to mention, is that this way of thinking about denoisers also has very close connections to the notion of score matching that has become really prominent in the machine learning literature as well. So let me take this description that I just wrote for you, f of x equals x minus the gradient of some scalar energy, and simply rewrite it. If I rewrite it, I get the gradient of e of x equals x minus f of x, and this right-hand side is, of course, the residual. So what does this mean? What's the interpretation? The interpretation is that on the left-hand side, if you think about it, if that e of x is somehow, that energy function is capturing something about the geometry of the manifold of images near x, then that gradient is effectively measuring the local geometry, essentially measuring the tangent space. And so what this means, and this is really very consistent with the interpretations and the intuitions that folks have given in the machine learning literature, the bottom line is that a good denoiser is learning the local geometry of the image manifold. And it means that a good denoiser is a good prior. And so I think it shouldn't be any surprise to anyone that denoisers find themselves to be so useful across the board, not only in imaging and image processing and computational photography, but also in computer vision and nowadays in machine learning. Okay, so now let me back up to some extent to some more practical matters and talk about how we can use denoisers to construct much more broad class of image filters. And then I'll go back to some theoretical issues towards the end of the talk. Okay, so what I want to say here is that denoisers are a very natural way of defining a splitting of the identity operator. And here's what I mean. So let's take the operator f, this denoiser, and apply it to x, and then look at the residual. Now, if I write x as f of x plus x minus f of x, I would presume nobody's going to object to that. That's an obvious statement. All I've done is I've taken the identity and I've split it into basically a smooth version and then a detailed version. Again, in the language of linear signal processing, this would be like doing a low pass filter and then keeping the high pass filter component, which is the complement. This is just sort of the nonlinear expression of the same. All right, now what I can do is I can take this first term where I computed the denoiser and I can repeat this process. So I can take f of x and apply f of x a second time and look at the residual of that. And I can repeat this process for as long as I want. And it will make sense so long as this f of x is non-expansive. As long as it's non-expansive, then the repeated applications of f are going to define a stable filter. And so the rest of the terms will also make sense. Now, let me be a little bit more general and think about the denoiser as a function of a bunch of parameters. Now, for example, you can take your denoiser and define the denoiser as a trained CNN, in which case this alpha would be the CNN weights that you're going to train for. Or it could be that you have a parametric or some other form of denoiser where you just have a bunch of control parameters that control the strength of the denoiser, and those could be the values in alpha, or any of the above. So in any event, I can write x equals f of x alpha plus the residual the same way. I've just added the parameter alpha here. And I can, again, repeat this process. So here I'm repeating this process. And so finally, after n steps, I write x as f applied n times. And then an accumulation of residuals, k equals 0 to n minus 1, where the residual is just the difference of applying the denoiser k times minus applying the denoiser k plus 1 times. Okay, so now that I have this, what I have is effectively a very general form of a decomposition of a signal, of an image, in a smooth component, and I have various control parameters. N is a control parameter. I can choose how many times I do this. And alpha is also a control parameter. I can choose how many times I do this. But now think about, if I have this decomposition, I can now recompose the signal X, but endow it with all kinds of operations that would otherwise be really non-trivial to do. So for instance, let me take these terms, and instead of just adding them as they are, I put coefficients beta in front of f to the n and beta k in front of the residual terms. Now what I have is a recomposition of that decomposition, and the images that I've generated in the family G, which are function of beta and alpha, now are going to span a very general class of images, all of which are related to X, but they have very, very different looks. And this means that I have now an engine that is able to do image processing for me with a set of parameters for any given image. So here's kind of what this might look like. I can do learning on this in a fairly straightforward way. I can take a pair of examples where this xi hat may be a very sophisticated processing, let's say through Photoshop, of the images xi, and I can just learn or kind of reverse engineer what that process is by learning with this loss function. The first term would be the training error, and the second term would be a regularization that I would apply to the network weights and these coefficient combinations. So what would I get out of this? Let me show you some examples that will hopefully convince you this is actually pretty useful stuff. So you start with the input image. You can push the input image through, I've written this here in terms of the linear or the pseudo-linear terms, but you can push the filter through various components and then combine them together. In fact, you can put nonlinearities in these terms as well. And now this is beginning to look like an actual neural network that you can train. And so you have the input, and you can produce high definition or high dynamic range outputs from it. There are various other visual effects you can produce. So let's say here's a picture of an old gentleman. What I've done here, there was no noise actually. This was a very clean image, professionally taken by Andre Dragan, who's a terrific photographer. Here, what we did is we just reduced the wrinkles, right? We trained filters that simply reduced the wrinkles. And we also cartoonized. These are all basically the same structure of the filters, just different sets of coefficients will do these crazy things. And all we have at the core of this is a denoiser. Here's another example, extending the dynamic range, expanding the dynamic range. Here's another example of getting rid of haze. This is particularly useful in machine vision applications. I know in Raquel's talk just prior to mine, she was talking about detection in haze. Now imagine if you go from here to here, you could probably do much more accurate detection once you reduce the haze. And it's a very, very straightforward way of reducing haze using these filters. Okay, so now I've come to regularization by denoising. So again, let me quickly review what I said. I talked about a general framework of what denoisers are like, what kinds of things we can do with them, some of the practical filtering things that we can do with them. And some of those are in fact used in the work that we've done with my team in very practical scenarios at Google. Here, this is a much more kind of conceptual, theoretical framework. And what we'd like to do is to use the denoisers for regularizing general inverse problems. So let me describe what this means in a very general way first that I'm sure you'll all be familiar with. So let's say you have an inverse problem you want to solve. You have x and y, which you're trying to keep close to each other. This could be denoising, in which case this would simply be x minus y some norm squared, or it could be some other inverse problem where the y might be related to x with some other operator. And the second term is a regularization. A very well-known and well-trodden path has been for people to use as regularizer the linear Laplacian operator. So this L here that you see is a very specific L in my case. All of these citations that you see down here are using the kind of pseudo-linear filters that we talked about here. But very early on, people simply used the linear Laplacian operator that didn't depend on x. Okay, so let's say if we do this, what are some of the disadvantages? Well, the Laplacian matrix is hard to compute directly. It's giant matrix. It's hard to work with, especially if it depends on x. But we can kind of get around that by, if we're solving this problem in an iterative way, in each iteration, we can compute L of x and then keep it fixed and then treat that as a fixed matrix so that L becomes essentially constant, and then we can take the next step and update it and so on and so forth. But if we do that, then we're kind of cheating a little bit. We don't know what energy is being minimized. So what we did next was an attempt to try to formalize this and understand what happens if instead of a general Laplacian here, we actually appeal to the general idea of a much more free-form denoiser. So what we did is we took this Laplacian regularization, which is this form of x transpose Lx is just x minus w of x. And we said, you know what? This w of x is just a denoiser. So why don't we just throw away wx and just replace it with a general f of x? Okay, so now what you have is the regularization is the inner product of x with the residual. And f of x is more or less arbitrary. Now, as you see later, in order for us to prove things, we had to put some constraints on what f is, but I'll get to that in a moment. Now, this second term, this regularization, is going to be small or zero in three different ways. Could be a zero or small in three different ways. X could be zero. This is really not of interest. X could be a fixed point of the denoiser, x equals f of x, or there could be orthogonality between x and the residual. And we'll see how each of these manifests itself in the next few steps that I'll describe. So now, as I said, in order to do this, in order to be useful, this had to allow us to compute the gradient of that regularization term. So we had to obviously assume differentiability of x. We also made another assumption, which is local homogeneity. That simply means that your denoiser has to be such that if you take the image and you scale it by a constant that is around 1, then that constant would simply come out. Okay, now it turns out not all denoisers satisfy this. In fact, many of them don't. But this was what allowed us to prove some things. And the other thing is Jacobian symmetry. And I put this little star here because I want to remind you that earlier when I talked about building denoisers from an energy model, that actually naturally gave rise to Jacobian symmetry. And finally, for convexity, we require passivity of the filter, which is something that I talked about earlier as well. Now, you might look at this and say, well, these seem all, pretty restrictive. And I would agree with you, except for the fact that practical experience showed us that almost any denoiser, including the median, any CNN you like, and so on and so forth, even if they violate these conditions, they seem to work in this framework. This is an open problem. We don't understand exactly why that happens, but it is an interesting framework and there's a lot of open problems. All right, so what are the implications of some of these assumptions? Well, of course, the differentiability is obvious. The homogeneity means that the directional derivative, f of x, can be written as its own directional derivative in the direction x. This is a kind of a peculiar property that these filters will have if they satisfy these conditions. But if you think about it, it's actually related to what I said earlier with the pseudo-linear denoisers. F of x equals w of x times x. if you look, the W of X corresponds to the gradient of F of X here. So this is just a more general way of defining essentially these pseudo-linear filters. And finally, the homogeneity implies a stability, that if you just simply perturb X by a little bit, then the gradient of the filter doesn't change a whole lot. All right, so what does this all mean? It means that if I actually take the gradient of R under these conditions, I can make a few substitutions and use all these properties that I just talked about. The bottom line is this last statement here. The gradient of the regularization term is in fact the filter residual. And so what that means is you actually don't have to compute a gradient at all. The gradient is this trivial thing, X minus F of X. So when you regularize, what you're going to do is when you differentiate this term, the first term here, for example, for a general inverse problem, this term should be easy to differentiate. And the second term is trivial because the gradient of this term is just X minus F of X under the conditions that I just described. So we have easy access to the gradient of the objective. Under the conditions that I mentioned, the objective is convex, and we can leverage powerful optimization algorithms. And again, what if our assumptions are violated? Again, practical experience has shown us that while many denoisers satisfy these conditions, though even for those that don't, the framework tends to still work. And that's where a lot of work still needs to be done. All right, so for this particular case, let's go through and actually carry out a fixed point optimization and see how this would work. So the derivative of this first term is H transpose HX minus Y. I guess there's a 1/2 missing there, but sorry about that. And then the second term, lambda times X minus F of X, which as I said is the gradient of the second term. And then I'm just going to put indices on xk and xk plus 1 and then rearrange the terms. And we see at the bottom here is xk plus 1 is a matrix inverse times H transpose Y plus lambda F of xk. And this thing is guaranteed to converge as long as F of X is passive, as long as F of X is not energy expanding. Let me rewrite this in a slightly more clean form so you can kind of see what this is doing. Xk plus 1 is equal to this term here in the first red square, red rectangle, is fixed. You can think of it as just a bias. It's in terms of the input data. You can compute it once and leave it alone. You'd never have to compute it again. And then the second term, there is a fixed matrix here. And that matrix is just, you can think of it as a linear filter. It's a convolution. And then F of X is the nonlinearity, which in this case is the denoiser. So I can write this in terms of block diagrams as X goes through F, goes through M, a bias is added, and then X plus 1 is produced. A little bit more familiar way to do this is to write it in terms of some auxiliary variables. So think about the output of the filter F as being these variables called Z. And I'm just going to rewrite the iterations that I had before in terms of Z's instead of writing them in terms of X. It's a trivial thing. It's just manipulation algebra. So if I do that, I can write in this fashion. And what you see here is that ZK comes in, a convolution is applied to it, a bias is added, and nonlinearity is applied. And then the same thing is repeated again and again. And so you have ZK plus 1 equals nonlinearity applied to convolution applied to Z plus a bias. This looks pretty much exactly like a neural network architecture, the CNN architecture that you're familiar with, except for the fact that the nonlinearity here is not a pointwise nonlinearity. The nonlinearity here could be global, it could be local, it could be involving multiple pixels, et cetera, et cetera. And the denoiser itself, this nonlinearity itself could be learned as well. So you could learn M, you could learn B, and you could learn F. And this is, if you go all the way back to Gregor and Lecun's work on learned ISTA, there are some relationships here as well, which I don't have too much time to get into. Okay, so let's show you some examples. The top left image is a ground truth. The middle top image is the blurred version. Our reconstructions are the two on the right-hand side, using a median filter as the denoiser and then using TNRD as a denoiser. The image on the bottom middle is using a method called plug and play. Plug and play is effectively writing the solution to an ADMM solution to the map estimation problem, and taking one of the steps of the ADMM that looks like a proximal operator and replacing it with a denoiser. This is a very popular method now called plug and play, and it was actually kind of quite an inspiration for us to work on RED, having seen that. The results are very competitive, even though the two methods are quite different. Although it turns out under certain circumstances, they can be understood to be doing the same thing. Okay, here's another example. This is 3x super resolution. The top image there is downscaled, blurred and downscaled, and then upscaled using bicubic, and then the one on the bottom right is our reconstruction. So what about some open problems? I mentioned this a couple times again. I will say it again. You may have denoisers that are that don't have a symmetric Jacobian. I would say that this is one of the probably most important technical issues, but it is not as important from a practical point of view. We see that these filters, even though most of them may not have symmetric Jacobians, still seem to work. Rehorst and Schnitter followed our paper pretty quickly and showed that if that symmetric Jacobian doesn't hold, then there's no direct regularizer that can have this gradient. The score matching, it turns out to be another alternative to understanding what happens with the RED approach when there is no symmetric Jacobian. Most recently, we've written a paper with Regev Cohen and Miki Alad that tries to unify the plug and play prior and the RED approaches and show conditions under which the two can coincide. And it offers increased flexibility in choosing the denoisers. The conditions that this paper requires of the denoiser are more relaxed than the conditions that we required in the original RED paper. And it provides global convergence guaranteed under more relaxed conditions. So I think with this, I can offer you some conclusions and maybe open it for questions here. So first thing, I hope I've managed to convince you that denoisers are a fundamental building block in many areas that most of us work in. I often joke that I think denoisers are as important to imaging and computer vision and machine learning as the Fourier transform is to signal processing. Maybe I'm not alone in thinking that, but that's my message here. In terms of form, denoisers are stable perturbations of identity. And we talked about that some. And in terms of generality, they can solve many problems, but also there are many challenges that remain. So I've given you some idea of what I think are insights that denoisers give into the nature of images. Very generally speaking, some of that has also surfaced in the machine learning literature, but there are many things that still remain. So I think even though we're done kind of with the quality of denoising, not getting a whole lot better, the kinds of things that we can do with denoisers and the interpretation learning that we can get from denoisers still remains very much an open area of work. And with that, I think I will stop. So thank you very much.